Hi, this simulation helps us visualize how voltages across a resistor, inductor, and capacitor change with time in an AC-driven circuit. So, if this were just a DC voltage, we would just add the voltage here plus the voltage across the inductor plus the voltage across the capacitor, and that would give us the total voltage across. But since these are time-dependent voltages, we can't just add the magnitudes. We have to actually add them, and you'll see we have to add them as vectors. So, let's use phasors to understand this a little bit better. If you've seen phasors before, this should be very straightforward. If you haven't, hopefully I'll be able to explain it to you. So how do we generate let's say a sine omega t function? Well, what we can do is if we take a vector, for example, this red vector here, which represents the voltage across a resistor, and we rotate it in the positive theta direction, omega t, sine omega t, and we project it onto the vertical axis, that will give us a sine function. Okay, and here we have, this is going at around 10 hertz. Let me increase this to about 20 hertz. Okay, so it goes a little bit faster. And now you see there are three voltages here that we're going to be looking at. The red represents the voltage across the resistor. The blue is the voltage across the inductor. Notice it leads the voltage across the resistor by about 90 degrees. And the green vector is the voltage across the capacitor, which lags behind the voltage on the resistor. And please note that the current through the whole circuit is the same everywhere, and it is going to be in sync with the voltage across the resistor, because when the current is big, the voltage drop across the resistance is big. When the current is small, the voltage drop across the resistor is small. So the current will be in phase with this red vector, and all we're doing is we're projecting these three vectors onto the vertical axis. And as we do that, we plot them up here at increasing time. So let's take a look at this. Let's keep this running. You can see red, here it hits a maximum. The projection gets smaller. Then here it goes negative, and that's going negative over here. The green, you can see, goes to 0 here. And now its vertical projection is negative. And the blue has a maximum positive, and it's starting to go down. So you can see you got these three vectors correspond to these three sine waves, and by putting different angles between them, we shift these phases. Now, the black vector represents the total voltage across the circuit, and that's being provided by this AC generator. So you can see right now, at low frequencies, the capacitor has the biggest voltage across it because it has a big impedance at low frequency, because its impedance goes like 1 over omega. So at small frequencies, most of the voltage drop will be across the capacitor, which is acting kind of like an open circuit, and you get very little current flow, which is proportional to VR. VR is proportional to the current flow, because basically the impedance of the capacitor is keeping current from flowing. Okay, so now let's reset this and start over and look at what happens as we increase frequency. Okay, so we're going to start at 20. And let's start increasing the frequency. The resistance is 1 ohm, the capacitance is 2 millifarads, and the inductance is 5 millifarads. So 22 frequency hertz, 24. And as we're increasing the frequency, you'll notice a couple things happening. This thing is spinning faster because it's at a higher frequency. The blue vector is getting bigger because the impedance of the inductor is getting bigger, because it goes like omega times L. Okay, and these will start the blue and the green will start canceling each other out. So let's keep going. Higher frequency still. Notice the voltage across the resistor is getting bigger, and when you add all three together, no longer is the total voltage over here, it's actually moving closer to align with the red voltage across the resistor, because the green and the blue are starting to cancel each other out. So let's keep going. Higher. Higher, a little bit higher still, higher frequency, 49, right around 50 hertz. Do you see what happens at 50 hertz? At 50 hertz, the voltage across the capacitor and the voltage across the inductor exactly cancel, and they give you a voltage, total voltage, which lines up exactly with the voltage across the resistor. And you can see over here, the red and the black are lined up with each other, and the blue and the green are exactly out of phase. They're canceling. See, this blue up here is canceling this green down here. Okay, and that's resonance. And you can see you started with a very small voltage across the resistor here. It got bigger and bigger and bigger, and now it reaches a maximum when these two cancel. Because basically, the only impedance you have now is the resistance of the resistor. The impedances of the capacitor and inductor totally cancel, and so you have the least amount of resistance to the flow of current. So let's go ahead and continue increasing the frequency. Now you can see the inductor is starting to dominate. Let me pause it. And you can see the inductor is now dominating because the inductor doesn't like high frequencies. It has a bigger impedance at high frequencies. It opposes those fast changes in voltage, and because its impedance goes like omega times L, and it's going to start opposing the AC current that's trying to flow through the circuit. And you can see now the total voltage is now tipped towards the inductor side rather than being over here on the capacitor side. Let's keep going to higher frequencies. And we keep going higher and higher. And let's pause it again. And let's do a close-up of what this looks like over here. So let's do a close-up of, let's go to 180 here. Okay? And you can see now the black and the blue tend to be more lined up with each other. The blue, of course, is the inductor voltage, is leading the total voltage, which is in black. And you can see the right here, you've got a positive capacitor voltage, and that's going to be this positive projection over here. You've got a slightly negative resistance voltage, which is down here, and then this is down, this corresponds to this, and the blue corresponds to this here. Okay, so what you really have to do is you just have to add these three vectors, the green, the red, and the blue, and when you add them as vectors, you get the black, and then you just project everything on the vertical scale, and you get these nice sine waves that are shifted from each other, with the shifts depending on the phase differences between these, or the angular differences between these vectors. Let me continue here. All right, so let's do something else. Let's set the frequency down to, let's say, 57. Okay, so we have slightly more on the inductor side. The inductor is starting to dominate. So what we can do is let's decrease the inductor value. We can change all these values. So let's decrease it a little bit. Do you see when I go from 5 to 4? Now all of a sudden the red, the blue, and the green cancel each other out. We're back in resonance. So by changing the inductor value to 4, we now move the resonant frequency up to about 57. And remember, the resonant frequency goes 1 over square root of L times C. So if I make L smaller or C smaller, I'll increase the frequency. And again, if we stop it and we take a look, we'll see we're on resonance, and we know we're on resonance because, let's take a closer look at this here. Let's zoom in on this. Let's go to maybe 85. You can see very nicely the capacitor voltage is exactly canceling the inductor voltage, which is in blue, is exactly canceling the capacitor voltage, which is in green. And you can see they cancel as vectors over here. They're 180 degrees apart in phase. And the resistance across the voltage across resistor and the total voltage are following each other exactly. And in this case, the total voltage is also in sync with the current. Because remember, the current is exactly in phase with the resistor voltage. And in this particular case, it's as if you don't even have an inductor and capacitor here. They just totally cancel each other out, and the only thing that's limiting the current is this resistor here. So it looks just like a basic driven single resistance circuit. All right, I hope this was helpful.